Welcome to your first flipped lesson. Quickly going to review the photoelectric effect introduction. And remember, it's about the particle property of light. What happens is that when light shines on a surface, a metal surface, it can cause electrons to be ejected from the metal if it's the right type of metal and if the frequency is high enough, in other words, above the threshold frequency. We know Albert Einstein's influence on this work, and we also know he decided to call these individual light particles photons. And a few years later, Louis de Broglie suggested the shape of the photon particle may be drawn like this. The demonstration circuit we're going to use throughout the slide presentation is simply an evacuated glass tube with 2 electrodes. This was where the metal is that's going to be used, and the incident photons or incident light on it at a certain frequency, and that will free an electron which then moves across the gap due to the electrostatic attraction that is between the 2 plates, and that will then set up a current. Remember to stop the video at any point if you want to just look at the diagrams more carefully or read over what's on the slides. Remember to copy down into your notebooks whatever's in orange. So again, you will want to pause the slides to copy that at the end of each slide. So the current of the ejected photoelectrons, we can call them just electrons from now on, does not depend on the voltage between the plates, right? So remember, the size of the current does depend upon the number of photons striking the plate. So for every photon that is incident, there'll be 1 electron. So the more photons that are incident, the more electrons released. Right? So in other words, that depends on the intensity of the light. So looking down here at the graph, you can see that the line drawn here is for dim light, and if we compared it for bright light, it will produce a greater current, assuming this is the same frequency. So the kinetic energy of the electron does depend on the voltage between the plates. And you know from level 2 electricity, the voltage is equal to energy over charge. And so from that, we can rearrange it. So EK equals E times V. Where did we get the E from? That is the charge on an electron, which is 1.6 times 10 to the minus 19 coulombs for each electron. So to measure the voltage of a photovoltaic cell, we adjust the variable power supply in this diagram. So we take the rheostat here and we adjust the supply and we oppose the voltage. So the opposing voltage is increased, in other words, until the current is such that no more electrons cross the gap. In other words, the current drops just to 0. And that is when the voltage across the supply will equal the voltage across the photovoltaic cell. Now this is done because the voltage cannot be measured directly across the photovoltaic cell, so we need to use the supply in order to determine what the cutoff voltage is. So remember, the increasing voltage, when it's turned to negative or opposing, stops the least energetic electrons from crossing the gap, and that eventually reduces the current in the circuit. So if we were to view this effect on a current against voltage graph for a specific frequency and intensity of light, it could look like this one below. So below 0 degrees, on 0 voltage rather, on the x-axis, the voltage is just opposing as it gets less and less, as fewer and fewer electrons are able to flow across the gap. And this point on the x-intercept is called the cutoff voltage, in other words VC, and that has been reached. And what happens if we change the frequency? The fact that the current falls to zero only slowly as the reverse voltage increases indicates that the photoelectrons are emitted from the metal surface with varying amounts of energy, right? So if we change the frequency, different intensities of the same frequency have the same cutoff voltages, but different frequencies or different metals will have different cutoff voltages. And that could be a different metal again. Just to keep in mind that frequency is inversely proportional to wavelength. So you look over here at violet. Violet has a large frequency comparison to red light, and the wavelength over here is smaller comparison to red light again. So as you decrease the frequency, you're increasing the wavelength. Keep that in mind. So we're going to look at the cutoff voltage against frequency. Oh, that's hiding behind the picture there. So again, we're using the same setup, and we're going to measure the cutoff voltage with a specific metal and different frequencies. So imagine we shone a ultraviolet light or violet light on a metal, and we measured the voltage of that. So the working cutoff voltage, and we did the same then for blue light, we did the same for green light, we plotted them onto a graph, we drew a straight line. Then the x-intercept will be what we call the threshold frequency, below which no electrons will be given off. So the energy will just be absorbed. In that case, if the frequency, any frequency below that, let's say a red light, was shone onto the metal, then it would just heat the metal up. And so what we can do is we can extrapolate that line, and the cutoff voltage can be found, V0. So it's another way of determining the cutoff voltage. The kinetic energy against frequency graph can look exactly the same, or will look exactly the same. So we already know that if we redraw this graph, in other words, we use this equation EK equals EV. We've just drawn the VF graph, voltage against frequency. Now we're going to draw the EK against F graph using exactly the same data. Okay, now the graph will show the maximum kinetic energy of the emitted electrons against the frequency. So down at the bottom again, if we extrapolate, we will find on the y-intercept that there is a minimum energy needed for the electrons to escape from this metal, and that there is called the work function. Remember that E is equal to HF, in other words, the energy of the photon. Don't forget that's what that equation stands for. So if we look at this graph, then the gradient, you can tell from H is equal to E over F, will be Planck's constant. Right, so for this graph, if you think y equals mx plus c, y is EK, m is your gradient, x is F, and y negative phi, because there's a negative y-intercept. Remember that symbol there is phi, or otherwise the work function, and there's a negative intercept here. So the equation gives the maximum kinetic energy of an electron. So when the electron leaves the surface, it will lose the work function, or lose energy. And so that's why it's negative. If we replace the metal with different metals, so this plate over here, then the graph for different metals looks different, but the slope is the same, which is H, and only the values for the threshold frequency and the work function will be different. And also remember that at this point, F0, or threshold frequency, the emitted electrons will have no kinetic energy, and so we can rearrange that equation where EK is equal to 0. We can rearrange it so that we can find the relationship between the work function and the threshold frequency. That's it. You can do the questions from the slide.